All right, so we have provide a systematic IUPAC name for the compound below. This is the one that was on the board. We talked about this in office hours, but remember these two bromines are in the plane. He's asking us about this chiral center, and he wants us to name it based off of that. So first, let me just name my chain. Let me number my chain. I see these two bromines here. That's a good indicator. That's where I should start. They're closest to the first carbon. In fact, they're on the first carbon. So that's 1, 2, 3, 4, and 5. So this is a pentane. All right, now we've got bromine, bromine. That's 1, 2. I'm sorry, that's 1, 1 dibromo. And we have 3 methyl. 3 methyl. And now we want to give it RS. I'm going to finish just naming this really quickly. So we've got dibromo is going to be our first one because of the B. Bromo comes before methyl in the alphabet. So we've got 1, 1 dibromo dash 3 methyl pentane. And now we need to figure out which way the chiral center turns. So let's erase all of my numbers and let's just look at our chiral center. All right, so we've got an invisible hydrogen that's in the back here. And so we can really just ignore it. I'm going to erase it because we're only going to be looking at these 3. So we have a methyl, that means methyl's 3. And we've got a C, and they're the same. They're CHH, CHH. So we're going to move to the next carbon. That's this carbon and this carbon. This carbon's HHH, and this carbon is bromine, bromine, hydrogen. There is an invisible hydrogen here as well. So this one wins over this one. So now we have 1. Let me get my green back. 1, 2. I'll erase all my scribble scratch here. So 1, 2, 3, and 4 is in the back. That's good. That's where you want it. 1, 2, 3. This is an S. And hydrogen's in the back. So it looks like S. It is S. So we're going to put S in front here. And this is the name. This is the proper name. Put the S. And you may even want to, I don't think you have to, but you may even do that. I don't think you have to though. I think that's plenty. That's just fine. All right, draw all possible stereoisomers of the compound shown below. Label any meso compounds. You must draw each isomer only once to receive full credit. Points will be deducted for any additional structures. Okay, here's how I attacked this problem. I started out by drawing on my piece of my answer key just a box of 4 because I have 2 chiral centers, one here and one here. And we know that our thing is our chiral centers equal n, and n 2 to the n equals the maximum number of diastereomers. Okay, so n is 2 here. So 2 to the second is 4. So there's 4 maximum possibles. So what I did was I drew out 1 first. So here's 1, 2, 3, 4. Our bromines. Let's just put them on wedges. That's just where I start. That's 1 compound. That's one way to draw it. If I were to draw a diastereomer for this, I would change 1, but not all. So I'm going to draw it again, and I'm going to change the first one. Now I have the diastereomer to this compound. Now, if I wanted to draw this, if I said I wanted to draw this, like if I wanted to change both, that would become an enantiomer. But this is the same compound. These two are. They're the same. Because if you were to flip it over and look at it from the back, it would be, depending on which one you looked at, if you looked at this one from the back, it would be this one. If you looked at this one from the back, it would be this one. So these are the same. So you can just like scratch this one out if you wanted to. And then we also have one more. We can draw the enantiomer of this compound. And that means we're going to change them both. So now we're going to say that this one is, like we're going to draw the mirror image, right? So let's just put a plane here and let's draw the mirror image of this one. So instead of having the first bromine on a wedge, we're going to look at, remember, a mirror image is going to be exactly opposite. So instead I'm going to put this one on a wedge because that's what's closest to me here. That's what's closest to me in this one. Those are closest. And then I'm going to put this one on the dash. So that's the enantiomer. So I'm going to draw that one right in here in my little box. All right, now, so this one is just the same as what I drew over here. Okay. Now, he also asks to label whichever one is meso. So we're looking for a plane of symmetry. Remember that anything that's trans can't be symmetrical. So, but this one's not trans. This one has a line of symmetry. You could, fold this in half and it would be exactly the same. So this one is meso. The other ones aren't. And we've eliminated one of them as the same compound. So you should have 3. Remember, 4 is the maximum, but we ended up with the same compound for one of them. So this is the correct answer. That's how you do it. Start with 1, change one thing, or or change both things. It just depends on how you want to do it. You could have also done it like this, where you drew the one thing and then you drew the exact, you changed both of them to try to get an enantiomer. And then you realize, hey, this is the same compound. Okay, so that's out. That's the same compound. What if I drew 1 forward and 1 backwards, or 1 backwards and 1 forwards? Okay, that's different. And what if I draw the mirror image to that? 1 forward, 1 backwards. Yeah, that's different. And these will have different chirality centers. These will turn in different directions. These two and these two, they'll turn in different directions. So this is the answer. Just make sure if you draw all of them, just make sure you scratch one out. If it's the same, you have to be able to identify the same. Where these two are exactly the same as these two because they're symmetrical. There's a line of symmetry. All right. Write a complete mechanism using curved arrows for the transformation shown below. All right, so we've got this is a radical reaction. And I'm going to draw chlorine out. So chlorine bonded to chlorine plus the radical CH3. And I'm going to follow my arrows. So this chlorine, I'm only going to take 1 electron from this chlorine and bring it to the center. That means the other electron has to go to the other chlorine. So I draw this one in the center, and then this is going to meet up in the center with the other one. And now I'm going to follow my arrows, which there's a bond here, by the way. He's already given us the products, but I can follow my arrows and make sure. So I broke the bond between chlorine and chlorine, and I gave one of the chlorines an electron. So that means that 1 chlorine has to have that radical. Plus, I bonded together, that's CH3 and that's Cl. So now I have Cl bonded to CH3. There's no radicals left because I've created a bond out of 2 electrons. So this is what your answer should look like here. On the last one, sketch your reaction coordinate diagram. He wants us to sketch it. Free energy, he says it needs to be exergonic. It has to have a single microscopic step, which means no intermediates. And label both axes with this. Oh, label both axes. That's part of it. And then also label delta G naught and delta G double dagger. All right, so we have energy over here. We have time over here. Remember, a reaction happens over time, and it takes energy for a reaction to begin. He wants one intermediate, and he wants it to be exergonic, meaning that it's going to lose heat. So our products should be lower in energy than our reactants. That means they've lost heat. They've gone down in energy. We have no intermediates, so this is one transition state. Our transition is right here. And so it's our transition state. He didn't ask us to label that, but I'm going to just label it anyway. These are our products. And these are our reactants. Now, our delta G's. Our delta G naught is going to be the energy it took to get from the reactants to the products. So I'm going to erase this so we can draw an arrow. That's our delta G naught. This is the energy it took from reactants to products. Our transition, or our delta dagger, is our activation energy. It's how much energy did our reactants have to use, or how much energy our reactants needed to overcome to get the reaction started. So that's going to happen at that transition state to the reactants. And that's our delta G double dagger. We saw an example of a transition state with an intermediate up here. Is it right here? Yeah. So if we wanted to label this one, we would say, well, here's our transition states. And our products are lower than our reactants. So this is exergonic or exothermic, however you want to put it. I'm just going to call it exo. And we can say here, our products, our reactants came from here and they traveled all the way down here to get to products. That's our delta G naught. And then our reactants had to go here to here. That's delta G double dagger. This is the first one because there's a second one. Because we had to overcome this one hill to start the reaction, the first part of the reaction. But there's a second reaction that happens from the intermediates to the products, right? And so they get their own delta G double dagger. So this is its delta G double dagger. And they call that the second one because it's the second activation. It's the second transition. So your delta G double dagger, I'll go back down here. So let's do this. Delta G naught equals total energy to get from reactants to products. Delta G double dagger is the energy total, or let's just say it's the energy from reactants to transition state. And that's it. So just, study and be able to read, be able to read and label these. That's the biggest thing. It's really not as hard as it may look in the initial glance. So just be able to identify those parts. And that's it.